Hi and welcome. This is our session number 6. And last time, I was finishing the proof. So I finished the proof about the theorem of regarding the multilinear maps, their continuity. So just to recall, because this will be important. If E1, so let E1, En, and F be normed vector spaces. Any normed vector spaces, and consider F from the product of EI to F a multilinear map. So multilinear. So n linear in this case, because there are n spaces. And then the following are equivalent. So one, that F is continuous on the entirety of the product EI. Second is that F is continuous at 0, the origin. 3, that F is bounded as a multilinear map. So i.e. there exists an M positive such that for all x, it's true that the norm of F of x is less than or equal to M times the norm of x. Of course, with the appropriate norms. So a choice of a norm, and also a choice of a norm on the choice of a norm on an element x of the product. So a choice of a norm on the product spaces. And recall that last time we said, when we're working on the product of the EIs, the norm 1, norm 2, and norm infinity, which will be the most useful, are all equivalent. The fourth point is that F is bounded as a function, genuine boundedness, on the closed unit ball for norm infinity. So ball, norm infinity, center 0, radius 1. So these four things are equivalent to each other. I have proven that 1 is equivalent to 2 and 4, but I have not proven that 3 is equivalent to the rest. I just proved one way of the implications, but you can easily do the rest. So this is equivalent to this, and this is equivalent to the fourth point. So we're going to use these interchangeably to say that a certain multilinear map is continuous. Now, following that, I was talking about the norm, the operator norm of a multilinear map. So the third point, this kind of boundedness as a multilinear map, motivates the definition of a norm, operator norm, on the space of multilinear maps. So the definition, so let E1, En, and F be normed vector spaces. We denote by L of E1, comma E2, blah blah blah, comma En, semicolon F, the vector space of all bounded, bounded as multilinear maps or continuous, continuous n linear maps. Now, this can be turned into a normed vector space by defining the operator norm of a certain, of a given n linear map. So let F belong to L of E1, E2, blah blah blah, En, semicolon F. Define norm F, operator norm, to be the supremum, over norm x in infinity less than or equal to 1 of the norm of F of x. This thing is the least upper bound of the possible bounds in the sense of boundedness of multilinear maps, and we'll write often that the norm of F of x is less than or equal to the norm of F times the norm of x, which makes sense. But this thing here will be the operator norm, operator norm for F, a multilinear map. And this makes sense when F is continuous, or if you want bounded as a multilinear map. Otherwise, the norm F could be infinite. In fact, it's an if and only if thing, because if the norm of F is finite, we know already that it is well defined and it's bounded. So here are some examples. So Before these examples, there are two exercises. Okay, so exercise number 1, short exercises, super easy exercises. Okay, just gonna write them down. So exercise 1, prove that the operator norm defined above, okay, is a norm on the space of multilinear bounded maps. This is really super easy. It's just how you prove that the operator norm for linear maps is a norm, which turns this thing into a normed vector space. Okay. Second exercise is that prove that if F is a Banach space, then the space L of E1, comma En semicolon F is a Banach space as well under the operator norm. And the way to prove this is literally, okay, so proof, or how to do it, how to solve it, literally replicate, okay, the proof we did previously, okay, for the analogous statement for bounded linear maps. Okay, it's really literally the same proof. What differs is that you would have to verify that the map you are getting is multilinear. Then you would have to accommodate for the multilinear norm. Okay, but that's all that differs. It's really nothing to do now. Okay, so one example, one very important example of a bilinear mapping. So example. Okay, so as a reminder, we are now on page 23 in Cartan. Okay, this example talks about the composition operator. Okay, so let E, F, and G be 3 normed vector spaces. Okay, if I have a map F going from E to F and the map G going from F to G, okay, I would want to talk about the map G round F. And this will be a map going from E to G. Okay, all multilinear maps, of course. Linear maps. Okay, we're talking about linear maps. Okay, so G and F are linear maps. I would want to talk about this composition. Okay, and then the mapping I'm considering looks like this. So phi has domain L of L of FG, because I'm gonna compose G F. So L of FG cross L of EF, and it's gonna land in L of EG. Okay, and it's gonna associate to each pair F comma G. Okay, so little f is an element of this guy, and little g is an element of that guy. Okay, it's gonna associate the element, so phi of fg equals. I wanted to say this is g and this is f. Okay, sorry for the confusion. And yes, g is the one belonging to this, and f is the one belonging to this. Okay, so anyway, it's gonna associate to the pair gf. Okay, this is all artificial, okay, because it really depends what you want to compose first. You can do it the other way around, okay. So G round F, okay, the linear bounded map G round F, okay. So recall that L of stuff. Whenever I say L of something, I'm talking continuous, okay. It's never just about linear maps or multilinear maps. They are continuous. It should be continuous, okay. So this mapping actually is bilinear. And this is something that we talked about previously. So why? So first, why is phi bilinear? So let's detail some things. First of all, let's do phi of G1 plus G2 F. Okay, what's this thing? This is G1 plus G2 round F, right? And so let some X belong to the space of G, which is F. Okay. Also, I want to compose with F, so let me take something in the domain of F, which is E. Okay, and so look at G1 plus G2 composed with F evaluated at X. By definition, this is G1 plus G2 of F of X. Okay, and by definition of the addition of two functions, okay, this is just G1 of F of X plus G2 of F of X. Okay, here we are not using linearity or anything else. It just follows the definition of stuff. And this is G1 round F of x plus g2 round f of x, okay? And this is g1 round f plus g2 round f of x. And that's why g1 plus g2 round f is g1 round f plus g2 round f. So we verified that phi of g1 plus g2f is phi of g1f plus phi of g2f. Same story, but of course now you need to use the linearity of the functions, okay? So I'm gonna look at phi of g f1 plus f2, okay? So let some x again belong to E, okay? Then what's g round f1 plus f2 of x? This thing is by definition g of f1 plus f2 of x, which is by definition of additional functions g of f1 of x plus g plus f2 of x, okay? And since g is linear, okay, so that's where linearity comes, okay, it's linear, it's gonna be the same as g of f of f1 of x plus g of f2 of x, okay? And this thing is g round f1 of x plus g round f2 of x, which is g round f1 plus g round f2 of x. And that's why, okay, that's why you get that phi of g f1 plus f2, this is phi of g f1, first guy here, okay, plus phi of g f2, second guy here, okay? So that's why, of course, if you want to do the scalars, so scalars super easy as well, same story, okay, multiplying by a scalar. So that's why the map phi is bilinear, but moreover, the map phi in these particular spaces, okay, it's going to be a continuous map, okay? So why is this the case? I'm looking at phi of gf, okay, and I want to find out the norm of this thing, okay, compare it with the norm f times norm g. Okay, so let me look at phi of gf, okay, and the norm. This is just the norm of g round f by definition, okay? And this is one property that we talked about earlier, okay, when we were denoting things by gf for composition. This is less than or equal to the norm of g times the norm of f, okay? And yeah, so we know that this implies, okay, this naturally implies that the norm of phi is less than or equal to 1. Why is this the case? Because literally what this statement here is saying, okay, is that you have the constant m equal 1, okay, such that norm of phi of gf is less than or equal to m times the norm of g times the norm of f. And we know that the operator norm of a multilinear map is less than or equal to whichever constant m which satisfies this kind of thing. Okay, since this thing holds for all g and f, right? And so phi is indeed continuous, and norm of phi is less than or equal to 1. So operator norm is bounded by 1. Okay, now one more point, 1.9. Okay, so section 1.9, a quite really important point as well. Okay, the natural isometry, okay, connecting the two spaces L of E comma F semicolon G with the space L of E L of F G. Okay, now what are these two guys? Okay, this guy is the space of all bilinear continuous maps from E equals F to G, and this thing on the right, okay, is the space of all linear continuous maps from E to L of FG. Okay, why are these two things in a natural isometry? So let's look. When I'm taking some f belonging to L of E comma FG, f is a bilinear continuous map, right? So f looks something like f of xy. It's taking something from E and from F. Okay, this is an element of G. If I fix x0, let's say, okay, just to make things simpler. Here, fix x0 and look at f of x0 y. What's this map? This map is a function of y, right? It's going from, with abuse of notation, this is going from f to g, right? And it is linear, okay? And since f is a continuous, i.e. bounded multilinear map, This will imply that for all x0, it's true that f of x0y is itself, this function y maps to this, is bounded as well. Why? Norm of f of x0y is less than or equal to norm f times norm x0 times norm of y, right? So for any given fixed x0, if I'm looking at this map over here, I know that the map, okay, y maps to f of x0y has norm, operator norm, less than or equal to the norm of f times the norm of x0 from this very inequality here. Okay, so that's why in getting a continuous map which is linear and it's landing as a function inside G. So what's happening here? I'm taking x in E, I'm mapping it to f of x dot, this function, which is an element of L of fg, okay, as we just proved here. So literally I'm considering the L of E, semicolon, L of fg, right? This is how you go from the first space to the second space, and vice versa. You go from the second space to the first space. Now let's formalize this. Let's write it in some neat and rigorous terms. So consider, so after we gave the intuition, okay, so let's say this as a theorem or proposition, okay. Let E, F, G be any non-vector spaces, okay, then L of E, comma F, semicolon G is naturally, okay, is isometrically isomorphic to L of E, L of F, G, okay. So proof. Consider the map phi from the first one, L of E, F, G, to second one, which is L of E, semicolon, L of F, G, okay. Just as we did above. If you are given some f here, which is bilinear, okay, associate to it the phi of f, okay, which is gonna be a map from E to L of fg. What's this map gonna do? It's gonna take an x in E and it's gonna get you phi of f of x equal to f of x dot, okay? Or in the most explicit form, okay, let me rewrite this map phi. So I need some bigger space. So this is phi is going from L of E, F, G into let's make this shorter, into L of E, semicolon, L of F, semicolon, G. Okay, to each make this even shorter. I should have made it even shorter. Okay, so to each F here, associating phi of F, okay, which is a map from E to L of FG, okay, which is acting by sending each X here to the element phi of f of x, okay, which is a map from f to g, okay, which associates to each y phi of f of x of y equal to f of xy. Okay, so if you want this, this is large diagram, okay, it represents what the mapping phi is most formally, okay. So we would want to prove that this mapping phi is bijective, okay, and that it is it preserves the distances. So we might prove that phi is bijective, of course, and we want to prove that phi is a linear map. Okay, so we want to prove that phi is linear. Okay, we want to prove that phi is bijective, and I want to prove that the norm of phi is equal to 1. Okay, so let me do that. So first of all, why is phi a linear map? So phi linear. Okay, so consider some f and g belonging to, of course, since we always need to verify for the scalars as well, let's just do this trick. Okay, so let alpha and beta belong to R. Okay, and let f and g belong to L of E, comma f, semicolon g. Okay, what is phi of alpha f plus beta g of x of y? By definition, this thing is alpha f plus beta g, okay, of x comma y, right? Because these are bilinear, they take two variables. Okay, this is by definition alpha f of xy plus beta g of xy. Okay, and this thing is alpha f of xy, okay, plus beta g of xy, and this thing is phi of alpha f of x of y plus phi of beta g of x of y. Okay, and this is phi of alpha f of x plus phi of beta g. I'm going to do this sort of proof just one time so you can see it, but we're not going to do it every time. It's very time consuming and it's very mechanical. Okay, but just so you know how things look like when we want to prove them. Okay, of y. Okay, and this holds, so this thing holds for all y, right? So that's why it's true that phi of alpha f plus beta g, okay, of x is equal to phi of alpha f of x plus phi of beta g of x, which is just phi of alpha f plus phi of beta g of x. Okay, and since again x was arbitrary, this also allowed x, so that's why I conclude that phi of alpha f plus beta g equals phi of alpha f plus phi of beta g. Okay, and yeah, I forgot to take care of the scalars, but it's really the same thing. Okay, so here instead of writing instead of writing alpha f and writing it as phi of alpha f of xy, just write it as alpha phi of f of xy. It doesn't make any difference really, because this thing here is just alpha f of xy, right? And this thing is alpha phi of f of x of y. Okay, so it doesn't really matter, but we can remedy this thing. We can just say phi of alpha f of x of y. Okay, this is for alpha phi of f of x of y, and this solves this this thing. Okay, so phi is linear indeed. Okay, phi is linear. And the second point, want to prove that phi is bijective. Okay, so to do this, I'm gonna just exhibit the inverse, just as it's done in the book. Okay, because it's way less painful to do that. So let's construct the inverse from scratch. So psi goes from L of E semicolon L of FG and lands in L of E comma F semicolon G. Okay, it's taking, so psi is taking some F, okay, which is a linear map from E to L of FG. Okay, and it's doing this. Psi of F, okay, is gonna be defined by, it's gonna be a map from E cross F to G, and it's acting by psi of F of xy, okay, it's a bilinear map, okay, is given by just f of x, okay, of y. How does this make sense? So f of x, so f is from E to L of fg, right? And then if I'm taking an x in E, f of x is gonna be in L of fg. It's itself a mapping, and it takes as an argument some y in f. Okay, so that's the definition of my psi, and it's really very easy to prove that psi is the inverse of phi. To prove this, just let's consider phi round psi. Okay, let's try to prove that this is the identity map. So let's take some f. So let some f belong to the domain of psi, which is L of, so it's a linear map, so L of E semicolon L of F semicolon G, okay, a linear map from E to the linear maps from F to G. And let's look at phi round psi of F. Okay, this is phi of psi of F. Okay, let's take some x and y in the appropriate places they should be, and let's look at phi round psi of F, okay, of x of y, right? How does phi act? Well, looking at phi of psi of F to make things clear, okay, of x of y. That's how phi acts, okay? It takes, first of all, a bilinear map, okay, and it first evaluates it at x and then evaluates it at y, right? And then this is what? This is, by definition, okay, by just the definition of phi, this is psi of f, okay, of xy. This is the definition of phi. Now, what's psi of f of xy? By definition, okay, this thing is this. This is f of x of y. So see, this is f of x of y. But again, what is this thing? This is just this is just f. Okay, so this is literally f of x of y. Okay, where it's understood that first we are doing, so f is being applied to x and then being applied to y. Okay, let's compare these two expressions. Okay, this thing and this thing. Well, this tells me, okay, since this is true for all x and y in the appropriate domains, okay, this will tell me that phi around psi of f is just f, right? And this is the same as saying that phi around psi is the identity map, okay? Because this holds for all f. There was nothing special about the f we considered, okay? So, and vice versa, you prove that psi around phi is the identity map. It's not difficult, okay? So that's why phi is bijective. Okay, and the last thing we need to prove is that the norm of phi is equal to 1, or if you want that for all f, okay, the norm of phi of f is equal to the norm of f. Okay, that's what makes it an isometry. So what to do this? Okay, let's consider phi of f. Okay, let's remember how phi of f acts. It acts first on x and acts then on y. Right, and it produces f of xy when it does this. Okay, so I'm looking at the norm of phi of f of x of y. I'm looking at the norm of f of xy. Okay, and by definition of a bilinear, of a continuous bilinear map, which is so f is a continuous bilinear map, is less than or equal to the norm of f times the norm of x times the norm of y. Okay, and what does this tell me? Well, it tells me that the norm, so this is true for all y, right? So then this tells me that the norm of phi of f of x as a linear map, okay, is less than or equal to the norm of f times the norm of x, right? And since this holds for all x, this tells me that the norm of phi of f is in fact less than or equal to the norm of f. Okay, that's the first thing that I need. Okay. And well, this will tell me that the norm of phi is less than or equal to 1. Okay. On the other hand, let's look at the norm. So let me check psi. Okay, let me check the norm of psi. What's the norm of psi? So let's remember, psi is acting by taking. So it's taking a a linear map. Okay, from E to L of fg, and it's giving me a bilinear map. Okay, from E cross F to G. So let's look at psi of, so let F be bilinear, okay, bilinear, and let me look at psi of F, okay, of xy, okay, the norm of this thing. Well, this thing, by definition, the psi of f of xy, by definition, this is just f of x applied to y. Okay, the linear map f of x evaluated at the point y. Okay, and by definition of linearity, okay, this is of continuity of linear maps, less than or equal to the norm of f of x times the norm of y. Okay, but furthermore, by definition of linearity of the function f, okay, this is less than or equal to the norm of f times the norm of x times the norm of y. Okay, and of course, so remember that f is going from E, okay, it's going from E to L of fg, but it's inside L of E, L of fg, so it's a continuous map itself. Okay, in any case, so last thing we got this thing, okay, and psi of f is a bilinear map, right? And we got this thing, okay, multiplied by norm x, norm y, and from what we discussed previously, we know that this implies that the norm of psi of f is less than or equal to the norm of f. Okay, and since this is true for all f considered bilinear, okay, this implies that the norm of psi is less than or equal to 1. So that's the second thing I was looking for. So now what I have is that the norm of phi is less than or equal to 1, the norm of psi is less than or equal to 1, but okay, I know that phi around psi is the identity map, right? Or if you want psi around phi. So the norm of phi around psi, okay, is equal to the norm of the identity map, which is 1. Okay, but I know that norm of phi around psi, this is less than or equal to the norm of phi times the norm of psi. So what I get is that the norm of phi times the norm of psi is bigger or equal to 1. Why? Because, okay, this thing is less than or equal to this, okay, and this is itself equal to this, okay? So that's why this thing is going to be bigger than or equal to 1, okay? But I know that norm of phi times the norm of psi is less than or equal to 1, because both of norm phi and norm psi are less than or equal to 1, okay? So what I get is that the norm of phi times the norm of psi is squeezed between 1 and 1, right? Norm of phi, norm of psi less than or equal to 1. And this can only happen if the norm of phi times the norm of psi is equal to 1, okay? But what does this imply? So first of all, I know that the norm of phi, so this equation will imply that the norm of phi is equal to 1 over the norm of psi, right? But I know, but the norm of psi is something that I know is less than or equal to 1. So I get that the norm of phi, which is 1 over norm of psi, is bigger or equal to 1, okay? On the other hand, so but norm of phi is less than or equal to 1. That's something I know, right, from the beginning. So it's greater or equal to 1 and less than or equal to 1, so therefore norm of phi is equal to 1. Okay, and therefore phi is indeed an isometry. Okay, or phi is an isometry, or phi is isometric. Okay, so that's why therefore the space L of E, comma F, semicolon G is isometrically isomorphic to L of E, L of F, G. And what does this mean? Okay, of course, this guy over here is the simpler space. Okay, this one is a bit more complicated. You're taking an element X of E and you're producing a mapping, okay, with using an element of L of FG, which is again a mapping. So this one is a bit convoluted, but this one is straightforward, just a bilinear map from E cross F to G. So what this means for us is that whenever we encounter a linear map of this sort, we're gonna see how it happens with differentiability just in a bit. Okay, we can identify it with this thing over here. Okay, what you will find out, okay, is that this means that the double derivative of a function at a given point x0, which is gonna be an element of this space by nature, is gonna be identified with a bilinear map. Okay, and the same story can be said, of course, about if you have n-fold stuff like this, it's gonna be isometrically isomorphic to all the n linear forms, and you're gonna identify the nth order derivative with an n linear map. Okay, so the theorem will look like something like this. If you have L of E1, L of E2, L of blah blah blah, so you have many convoluted stuff. This is gonna be isometrically isomorphic to L of E1, En, semicolon F, which is just the n linear continuous mappings. Okay, so but we don't need to worry about this for now. Okay, let's just postpone this worry for later. Now we are in place to start with defining differentiability and talking about derivatives. Okay, which is our goal in this course. What we did so far was just building up for this. Okay, because literally everything that we have done so far is needed to talk about differentiability and to play around with derivatives. So finally, now we start with differentiability. Okay, differentiability. First, I'm gonna give a brief motivation for why we define differentiability in the way I'm gonna define it. So we're gonna be talking about a function f, which is defined on an open subset U of a known vector space E, and landing inside the known vector space F. Okay. But to motivate this definition, let me just recall what it means for a real valued function. Okay, so let's suppose, so example for intuition. Okay, let's say you have a function f defined on some open interval, okay, or an open set, whatever, inside R going to R. Okay, let's say there's some point A in I. Okay, what does it mean for f to be differentiable at the point A? Well, it means that there exists some real number f prime, we denote by f prime of A, okay, such that the limit as h goes to 0 of f of A plus h minus f of A divided by h is equal to f prime of A. Okay, This thing is just a symbol, okay, f prime of a, which is what we call the result of this limit, which should exist. So definition goes like this. This limit here should exist, and its value is what we call f prime of a. Okay. Now, if I want to generalize this to other situations, let's say h is a vector. Okay. So if h is a vector, can I actually divide by a vector? I mean, yes, if you are in an algebra and you're talking about an invertible element of this algebra, this can happen. But this is too specific, right? I don't want to be doing things that specifically. I would want to talk about a general vector h, okay, just moving around inside the non-vector space that I have. Okay, and I would want to make sense of this expression, okay, this entire expression that is equal to some number which exists. So unfortunately, I cannot divide by h anymore because h is a vector. Okay, I would need to find a way around this. So let's look at this fraction, f of a plus h minus f of a over h. Okay, I'm trying to say that this thing, which is a function of h, okay, is gonna be going as h goes to 0 to some number. Okay, let's call it for now. Okay, let's just keep calling it f prime of a. Okay, what does this mean? So that this thing is literally a function, okay, and I'm finding the limit of this function. So by definition of limit, this means that for all epsilon positive, okay, there is some delta positive such that whenever absolute h is less than delta, I'm still talking inside R here, okay, so that's why I'm using absolute h. Whenever absolute h is less than delta, okay, the absolute value of f of a plus h minus f of a divided by h minus f prime of a, okay, this thing is going to be less than epsilon. This is literally the definition of the limit of a function, okay? And if I want to rearrange this thing, okay, in such a way as to make the h in the denominator disappear, I would just naturally multiply both sides by absolute h, okay? So let's just multiply both sides of inequality by absolute h. And what do I get? I get that absolute h times f of a plus h minus f of a divided by h minus h times f prime of a is less than epsilon times absolute h. And now these things cancel out, okay, h with h, and what I'm left with is that absolute f of a plus h minus f of a minus h f prime of a, or let's rewrite it in a fancier manner, preparing for the general definition, f prime of a times h, okay, less than epsilon times absolute h, okay, and this is still equivalent. This is equivalent to the above, okay, it means the same thing. So if naturally, if I want to be generalizing this, okay, I'm going to be writing something like this, okay. Now, how do I make sense of the expression f prime of a h, okay? The way I'm going to make sense of this is I'm just going to say, okay, f prime times h is a linear map on R, okay? Why is it a linear map? It's a linear map of h, of course. So h maps to f prime of a times h. This thing is just a linear map on R, okay? And generally, I would want to be talking about linear maps, okay, and to make sense of the derivative, okay? So that's why we're going to lay out this definition, okay? So definition, and of course I'm going to give some particular cases which follow from this definition, okay? But after I just establish a few things about this definition. By the way it's done in Henri Catan's book, there's mention of this thing called tangential functions, tangentiality of functions, and there are some things done with that. I prefer really to not go into any of these because we really don't need this notion of being tangential to each other in order to define the derivative, okay? This is one way to define it. You talk about the tangential functions, but it is not a cute way to do it, okay? This thing is way better. So let's do the definition this way. So let E and F be any non-vector spaces, okay, with respective norms, okay? We don't need them to be Banach. We don't need any special assumptions, okay? So just any non-vector spaces. And let U subset of E be open, okay? Let F from U to F be a map, okay? Any map. So let A belong to U. We say that F is differentiable at A if there exists a linear continuous map L from E to F, okay, linear and continuous, or if you want, in other words, L belonging to L of EF in our notation, okay, such that for all epsilon positive, okay, there exists a delta positive such that if the norm of H is less than delta, then the norm of F of A plus H minus F of A minus L of H is less than epsilon times the norm of H, the complete analog to what we have done above, okay? So of course here you should understand that this is the norm on F, and this is the norm on E, okay? I'm just gonna write norm for everything, okay? Including operator norm and whatever, okay? It's gonna be clear from context which is the norm of what. So this is the definition of differentiability. Now, some things are due. First of all, you would ask, okay, does this guarantee that there is a unique derivative? Okay, so that's our first proposition. So proposition, in the above definition, okay, such an L is unique. Okay, and we write df of A for the mapping L, okay, and this thing we call the differential of F at the point A, and this is a linear map, okay, so pay attention to it. You take a point and you produce a map, okay, you don't produce an element of course a map is an element of some space, but like I mean, you don't get a genuine point like A again, you get a map, okay, full-fledged map. So this is a linear continuous map, okay, from E to F. And another note is that, notice that I said L is gonna be a linear map from E to F. We're not concerned with the U anymore when we talk about the L. Okay, the L should be defined on the entire vector space. It should be linear at the end of the day, of course. So it should be defined at least on a vector subspace. The U is not important anymore. The U could be not a subspace, not a linear subspace. It could be just an open set, whatever. Okay, but L, the derivative map, should be defined on the entire vector space E that we started with. Okay, so let's prove this thing. Okay, so suppose F is differentiable at A. Let L1 and L2 be two maps, okay, inside L of EF, such that the above definition applies. So such that it's true that for all epsilon positive there is a delta positive, such that if the norm of H less than delta, then the norm of F of A plus H minus F of A minus, just to not write this twice, I'm gonna write Li of H is less than epsilon times norm of H. This will hold for I equal 1 and I equal 2. Okay, and I would want from this thing to prove that L1 is equal to L2. So I require to prove that L is unique. So I to prove that L1 is the same as L2. Okay, what this means is that I need to prove that for all. So prove that for all H in E, L1 of H is equal to L2 of H. Okay. Usually when you're talking about a linear map, you don't put the parentheses, okay, just to simplify things. So let's just get used to this notation from now. L1H is just L1 of H, okay. So how do I prove this? Okay, very naturally I would be wanting to look at the norm of the operator. So notice that since L1 and L2 are both elements of L of EF, okay, L1 minus L2 is also an element of L of EF. It's also a linear continuous map, okay? So if I can prove that the norm of L1 minus L2 is equal to 0, I can conclude that L1 minus L2 is the 0 map, so L1 is equal to L2. Let me try to prove this thing, okay? So let me use the definition, okay? Let me use this definition, okay? For I equal 1 and 2, okay. By the way, although this is morally speaking correct, but to be more precise, let me write this. Let me write for all epsilon I positive, there is delta I positive, such that less than delta I, epsilon I, okay. And then, okay, I'm gonna say let epsilon positive, okay, so let epsilon positive be arbitrary. Okay. And I know that there exists some delta 1 and delta 2 positive such that blah blah blah, right? If the norm of h is less than delta 1, okay, respectively delta 2, then etc., right? And to make this simultaneously happen, okay, I will take delta 0 to be the minimum between delta 1 and delta 2, okay? I know that if the norm of h is less than delta 0, then it's true that the norm of f of a plus h minus f of a minus li of h is less than epsilon times the norm of h. Okay, and I know that this holds for both maps, right? So this is exactly correct. Okay, now I'm gonna look at the difference. Okay, so look at the difference. Norm L1 of h minus L2 of h. Okay, what's this? This is the same as the norm of L1h. Okay. Plus f of, or let me subtract here, so minus f of a plus h minus f of a plus f of a plus h minus f of a minus L2h. Okay, and now I'm going to use the triangle inequality. I'm going to say this is less than or equal to the norm of L1h minus f of a plus h minus f of a, okay, plus the norm of f of a plus h minus f of a minus L2h. But this thing here, okay, just multiply by a minus inside to turn it into what we want. Okay, so this is the same as the norm of f of a plus h minus f of a minus L1h plus the norm of f of a plus h minus f of a minus L2h. And I know, okay, I know by this thing here, okay, that both of these are going to be less than epsilon times the norm of h plus epsilon norm of h, which is 2 epsilon times the norm of h. Okay, so it holds true. So conclusion for now, for all h, if the norm of h is less than delta 0, okay, then the norm of L1, let me just to make things shorter, okay, L1 minus L2 of h, okay, is less than 2 epsilon times the norm of h. Now I'm not there yet. Okay, now let k belong to E, okay, be anything, okay, any vector. Of course, if k is 0, then that's a trivial case, as you will see, because this will imply that L1 minus L2 of k, which is 0, okay, is of course less than whatever you want, okay, less than whatever non-negative quantity you want. Okay, so suppose that k is non-zero. Okay, let's look at, so let h be equal to delta 0 over 2 norm k times k. Okay, what do we know about the norm of h? The norm of h is just delta 0 over 2, right, which is less than delta 0. And by assumption, this implies that the norm of L1 minus L2 of h is less than 2 epsilon norm of h. In other words, the norm of L1 minus L2 of what's h? Delta 0 over 2 norm k, okay, is less than 2 epsilon norm of delta 0 over 2 norm k, okay. And this, okay, if you take the scalars outside, this thing, remember, this thing L1 minus L2 is again a linear operator. So you can take things outside and then you can take them outside the norm, the scalars. So you get delta 0 over 2 norm k, okay, times norm of L1 minus L2 of k is less than 2 epsilon times, of course, the same story here, delta 0 over 2, okay, and then you have norm k over norm k, which will cancel out. Okay? So now, when we cancel stuff out, so delta 0 over 2 can be cancelled out for both sides, and then we take the norm k to the other side, so I get, therefore, norm of L1 minus L2 of k is less than 2 epsilon norm of k, okay, and this holds true for all k in E. If k is 0, it would be less than or equal, or it would be strictly less than again. Okay, so, but the k is 0, so it would be less than or equal, okay, for k equal to 0. Okay, but this really does not matter in any kind of way. So what I have is that the norm of L1 minus L2, an operator norm, is less than or equal to 2 epsilon, right? Because the operator norm of L1 minus L2, which is continuous, so I can talk about operator norm, is the infimum among all these stuff, okay, which bound it in the sense of a linear map. So, conclude, since epsilon was arbitrary, it's true that for all epsilon positive, the norm of L1 minus L2 is less than or equal to 2 epsilon. What does this mean? Okay, if you want to take epsilon to 0, if you want to argue using some other kind of way, the conclusion is that L1 minus L2, the norm is needing to be 0. Okay, and therefore L1 minus L2 is the 0 map, and therefore L1 is the same as L2. Okay, so indeed the derivative is unique. This linear map is unique, and we denote it by the derivative of f at a, df of a. Okay. Now, that's one thing, okay, for the uniqueness of the derivative. There are some other kind of things I wanted to talk about. So let me read out things from the book, okay, following the points in which there is mention of the this tangentiality, okay, the functions being tangential to each other, which is something that I really don't want to go into in any kind of way. We'll just ignore. Okay, so let's suppose that what's happening in Cartan is just that derivatives are defined this way that I've just laid out, because it really makes no difference. Okay. What are some important points though in the book following this tangential thing? So we have on page 26. Yeah. So what does it mean to be? There's an example where the domain is R, which we're going to talk about. Okay, but let me define what it means to be differentiable everywhere, and then what it means to be of class C1, and then we'll go to some examples. Okay, so definition. Okay, again, let f from U subset E to F, where it's understood that E and F are non-vector spaces. Okay, and U is open. Okay, so F is differentiable on all of U. Okay, if F is differentiable at each A in U. Okay, and if this is the case, okay, then there is a map well defined which you call df, okay, the differential of f, which is a map going from U, okay, into the space L of EF, which associates to each A in U df of A, which is a linear continuous map from E to F, okay, given by df of AH. So usually for the when I have the differential map, okay, this is the differential map in the sense of the genuine derivative of our map. df of A, okay, is the differential of f at A, which is itself a map, okay, which if I want to write things super neatly, I would say df as a map is applied to A, and then this thing is a map which is applied to H. But of course, this makes my life super miserable. So what I'm going to be doing is I'm just going to be writing df of AH. Okay, the notation used in the book of Cartan is just this, f prime of AH. Okay, and yeah, so this is the one I'm going to be using, df of A multiplied by H, where it's understood that multiplication is applying the map df of A to the vector H. Okay. Now another definition. So as usual, f from U subset E into F. U is open in E and F are non-vector spaces. Okay, F is of class C1 at a point A in U if it's true that, first of all, F is differentiable in a neighborhood V subset U of A, okay, and second of all, the differential map F, okay, which is defined on V where F is differentiable and landing in L of EF. Okay, this mapping dF itself as a map from V to L of EF is continuous. Okay, dF is continuous where at A, okay, which is already inside V. Okay, so F is differentiable on a neighborhood of the point, because if it's differentiable just at the point, you cannot talk about dF as a map. you just have df of a. You cannot talk about df as a map. Okay, so we want to guarantee that the function is differentiable in the neighborhood of the point. This is u, this is the point, differentiable somewhere here, f. Okay, and then you can define the differential map, okay, on this neighborhood v of a, and then you would talk about the continuity of this map df as a map going from v into L of ef. Okay, this is equipped with the norm of, this is of course understood to be an open subset of E, and then the norm on V, or the topology of V, is the one induced by E, okay, for the norm of E. And then the topology, of course, of the L of EF is given by the operator norm. Okay, this mapping, which is going from this space, this subspace V of E, subspace in the sense of topology and not in the sense of vector spaces, okay, into the space L of EF, is a continuous map. Okay, so that's what means to be of class C1. Of course, when we talk about higher order derivatives later, we will be defining what means to be of class C2, class C3, class C infinity, if you want it. Okay. So a particular example which will give us grounds to start with the exercises, which is going to be the content of the next session. The next session is completely about exercise. We're not going to be doing any notes. Okay. So this is something useful. So example. Okay. Let's say a function f, which is defined on an open subset of R, the real numbers with the Euclidean topology. Okay. Into a some vector space f, non-vector space f. Okay, what happens in this situation? In this situation, you can talk about perturbation of the h, which we were worrying about at the beginning. Okay, you can just talk about its perturbation as a scalar. You don't really need the definition of the epsilon and the norms and all whatever. Okay, so you would say that f is differentiable at a in u, which is going to be equivalent to the definition we gave in general as well. Okay, if it's true that the limit as h goes to 0 of 1 over h times f of a plus h minus f of a exists, I can talk about this thing. 1 over h is just a scalar, because h is a scalar, it's a real number. So I can talk about this limit, okay? And if it exists, I just denote it by df of a. Or if you want, just f prime of a. Okay, and now the special thing is that we know that the derivative map, so f is going from u subset R into f. So I know that the derivative map, okay, at a is going to be an element of L of Rf, right? But we saw last time, or in session 4, not sure exactly which one, L of Rf, okay, this thing is the same as f. Okay, this can be identified with f. So you're actually looking at an element. So you can look at df of a to be an element of f. And then we will talk about vector functions, quote-unquote vector functions. Okay, in the sense that we used to do with vector vector functions. So you'd have a function f, okay, let's say from R to R3, okay, which is given by, let's say, f of t in physics. You'd have encountered this in physics or in early courses in calculus. Okay, so given by, let's say, t squared sine t. Okay, then to find f prime of t, you would just do, okay, 1 to t cosine of t, right? Just differentiate each component. Okay, and in a sense, that's what we would like to understand about a function f, which is going from an open subset of R into some non-vector space f. Now, with the nuance that, of course, f is not supposed to be a finite dimensional vector space. It could be infinite dimensional, okay? And then there doesn't need to be components of the function that we are dealing with. So f of t, yes, it's going to be an element of f, but f does not need to be finite dimensional. So you don't have the privilege of writing f of t as some f1 of t, f2 of t, whatever. There are infinitely many components, so to speak, like what happens in infinite dimensional vector spaces. So that's not something that's going to happen unless f is finite dimensional. Okay, so this understanding is good to keep in mind regarding why we are doing things this way, but it's not going to be generally applicable, this kind of thing. Okay, but we would want to think, okay, and this is what we're going to be doing, because literally we can identify L of Rf with f, just like we proved once. Okay, and then when I talk about f prime of A, I'm going to be talking about an element of f. Okay, although it's a linear map from R to F, it's literally the same thing as an element of f. Because if you recall linear maps from R to F, well, you just write, okay, f of x equals what? Equals x times f of 1. And this is this unique element, okay, of f defines the function f. Okay, so f is the same really as f of 1 in this perspective. Okay, that's one note I wanted to give. Okay, and I guess so I'm just reading now from Kata to see if there's anything to mention. This is the Landau notation. Okay, the Landau notation, I would have wanted to talk about it a bit. Okay, and the equivalence of norms implying differentiability with respect to any of the two norms. These are really some simple things, but we ran out of time today. Let me just mention them very briefly, and maybe before starting with the exercises tomorrow, I'll just do these things and then go to the exercises. So first of all, the Landau notation. Okay, so what's the Landau notation? So you say that a function f of x, okay, say f is defined on some u subset e into f, non-vector spaces, okay, and use an open set. I say that, so let's say there's a point, let's say 0 belongs to u just for simplicity. You can always translate, okay, there's no difference. So we say that f of h equals to little o of h, or let's say generally little o of g of h for some function g. Okay, so this is the little o, or Landau notation. So Landau notation. Okay. If it's true that this fraction, so limit as h goes to 0 of norm f of h divided by norm g of h, this thing equals 0. Okay. Now the nice thing about Landau notation is that it really makes many things simpler to work with. Okay. Why? Because the Landau notation respects addition. Okay. Respects multiplication, okay, respects division, it respects even finite expansions. Okay, so I'm going to give a brief example about this. It respects integration, okay, and some really other cool things. Okay, let me give an example of the Landau notation just to give you a feeling of it. So let's say you're computing the limit as x goes to 0 of cosine x to the power 1 over x squared. Of course, when I directly substitute 0, this is just 1 to the power, this is 1 to the power infinity, which is an indeterminate form. Okay, so I would need to do something else. So cosine x to power 1 over x squared. Let me write it as exponential 1 over x squared len of cosine x. Now, of course, I can talk about len of cosine x because x is a neighborhood of 0, and so cosine x is guaranteed to be positive. Okay. Now, the thing len of cosine x is just len of 1 minus x squared over 2 plus little o of x cubed. Okay, why? Because the next term in the cosine series expansion is x4 over 4 factorial. And when you divide x4 by x cubed, you're going to get x, which goes to 0. Okay, so, and then this thing, okay, this is applying the rule of the Landau notation being compatible with finite expansions. This is just minus x squared over 2 plus little o of x cubed. Okay, and then I'm looking at 1 over x squared times minus x squared over 2 plus little o of x cubed. Okay, and then this is just minus half, and then supposing we know the rule that the Landau notation respects division, this is just little o of x. Okay, and then I have exponential minus half plus little o of x. Well, little o of x goes to 0 as x goes to 0. So this thing goes to e power minus half, i.e. 1 over radical e. So I got the limit. Okay. That's one of the ways to see how the Landau notation is useful. Now, of course, in the context of vector space, it's going to be different somehow, but it's going to have similar uses. Okay, so that's one thing, the Landau notation. Okay, and next time, before I start the exercises, I'm going to talk about when two norms are equivalent. Why is it true that differentiability for this is the same as differentiability for this? And I'm going to expand on Landau notation. Okay. Expand a bit, and then I'll start with the exercises, which are not, by the way, from Cartan's book. Okay, they're from the worksheets that I talked about in session 1. Okay, so thank you for watching today, and I'll see you next time.